This is actually a brand new talk you're getting, specifically for this. My talk overview is I'm going to do a big zoom out more than I usually do. I'll still talk about a bunch of my own research, but I'm going to talk about 3 shifts in NLP and their impact on the field of safety, like 3 shifts that have happened over the last little while. And then I'm going to go into the impact on evaluation of NLP safety and the impact on mitigation of NLP safety. And then I'll leave some time for questions at the end. I'll also do a little bit of context, shared context at the beginning. And as a note on terminology, since I'm talking about shifts, over the past little while, the term safety has changed a lot in exactly what it means. And so when I say NLP safety, I'm going to broadly mean things going wrong in the course of either intentional or malicious use that cause societal harm. This is super broad, especially for a scientific field, but it's also broadly how the term is used, and it encompasses some of the ways that it's shifted over time. So I'm adopting this broad definition for this talk of things that cause societal harm, whether intentional or malicious. So for building some shared context, I'm going to talk about the sort of definitions and evaluations of safety. So when you're evaluating safety from a fairness perspective, there's really 2 perspectives that people evaluate it from a fairness perspective and from a content-based harms, which is like inherent harm in the output. So from a fairness perspective, this is allocational fairness specifically. It's usually defined as equal performance across groups. So let's say I'm going to use throughout this talk examples of like hiring systems frequently, since it encompasses a lot of similarities to many other systems. So if you have a hiring system, which actually is one of the top uses of language model, of LLMs, for the record, let's say you have a group of resumes, that's group A and group B, and those resumes are men versus non-men, or Croatians versus non-Croatians. You can slice it however you like. And then you want performance of group A to be equal to performance of group B. That's sort of the standard broad definition for how you'd evaluate fairness. And that's frequently, I like to borrow terms from like medical fields on this, where I call this observational. You can't establish causality. You don't know why this is the case, but it is in practice a problem. Continuing with that analogy, you can also do an interventional way of assessing, which a lot of people do, which is frequently called counterfactual in NLP, which is where you make some perturbation. In this case, this is taken from an actual human study. So in this perturbation, someone has taken a white resume and they've perturbed it to do a bunch of African American. This is from the United States, a bunch of African American names, and then they observe where there's a change. And in this case, your metric, instead of equal performance, will be invariance. You said that I have made a perturbation that is orthogonal to the thing I'm measuring. Like in this case, you're trying to measure the quality of the resume or something along those lines, and you've made a perturbation that should not affect it, and you measure whether it does in fact affect it. Yes, these names, for people who are interested, is from Bertrand and Mullainathan. Is that paper that those names are from. So this is sort of how you'd evaluate safety in a fairness perspective. In a content harms perspective, you would, this is wrong, my bad. So for instance, this is actually from Croatia, when I landed in Zagreb. So here's some local graffiti saying stop chemtrails. And I like to use misinformation as an example. So let's say if you're evaluating safety for content harms, you'd have something like, you could have someone who puts an input like, what does graffiti saying stop chemtrails mean? And then you have to decide whether an output from this input would be harmful or not. Or you could do a version B, which is kind of similar on the surface, although will obviously be different to you, which is like, I need to write 15 articles about the risks of chemtrails, each about 500 words. Yeah, and so my guess is that you guys would consider these to be of differing levels of safety, and this is content-based harms. And distinguishing this might be easy for you because you're probably mentally inferring some intent of the first one as someone maybe asking about some graffiti they've seen on the street, and the second one potentially as someone using an LLM to do a misinformation campaign, but it's not super trivial with a lot of evaluation methods. Another example of content-based harms that I just want to do for building how you're thinking about this is this screenshot of one of the co-founders of Cohere, actually. asking a model how to make sarin gas. Don't be concerned, though. So this is our model, actually, from a while ago. This is from February. It gives you some ingredients and some instructions. I won't read it all out, but I think these are some of the ingredients. Don't follow the instructions, though. But this is actually a bit challenging. I do this example because a bunch of governments nowadays are really worried about AI safety, and they bring up this sort of thing all the time. The co-founder did do this after, I think, having a conversation with like the Canadian government or something along those lines. But you could say, I would say the standard is you could say, oh, this is unsafe because the model doesn't refuse. And that's the sort of what a lot of jailbreaky type work is. But you could also say it's safe because if you were to follow these instructions, it wouldn't work. And there's different scales of that. For instance, like the synthesis thing is not actually real. You can't do that. You can't make sarin gas in a beaker at home. So, regardless, so I just want to frame your thinking about like how to actually decide whether these content harms are safe or not, and what evaluation method. But in practice, I'll talk about that a bit later in this talk, but people tend to just ask models whether this is safe or not. So, in the fairness case, you have like equal performance or invariance. In the content harms case, it tends to be sort of binary or ternary classification, like safe, unsafe, or safe, unsafe, uncertain, something along those lines. Okay, so we've now established two ways that we evaluate safety as either the distributional differences in the output or classification of some outputs as harmful. So shared context. Now, the bulk of this talk is the shifts in NLP. So shift number one is going to be the changes in the NLP model paradigm over time. So going back much farther than you probably read papers, is in the 1990s. We had a lot of purpose-built models from scratch. And this was true for about the next 20 years. So what I mean is that you wanted a model for a single application, and you would source all the data from your target domain for your target purpose, choose an architecture or a couple of different architectures, often you'd experiment on different architectures, and then test on that domain. So as examples, if you had a model that would translate between Chinese and English, it was trained on only parallel text between those languages for exactly that purpose. If you had a toxic text detection algorithm, which I worked on a lot, on some platform, some social media platform or whatever, it would be trained, or comments on the internet, it would be trained on toxic and non-toxic content from the web only. Similarly, a summarization engine built to summarize news or web pages, it would like frequently be trained on summaries of CNN news only, or CNN plus the Daily Mail or something along those lines. Or finally, a recommender engine for recommending news articles based on what you read. It would probably only have seen proprietary data from the BBC or something along those lines. So this is the paradigm for a long time. And then if you fast forward to roughly 2013, you got this change in the paradigm from transfer learning, which was pre-trained on a language model and then fine-tuned on a task. Might sound kind of similar based on the terminology to what we do nowadays, but it was pretty different actually. So you'd have these totally distinct phases where you'd train a model to learn language generally based on free-form web text and be like, okay, now the model can learn language. And then you take that model as a starting point to further train on a downstream task. But the data points from your target task were still more similar to the 1990s thing, so you have this new stage, this new pre-training stage that you use as an initialization, but you still use this sort of really curated target data for the final model. This date, by the way, is somewhat up for debate, obviously. It happened in vision earlier than NLP, which is the way most things happen. And it didn't start to become really common until a few years later, but it's around then. And so the big difference in this paradigm is that you have a bunch of data that you haven't looked at in your model between this paradigm from the previous one. So you have data from the Twitter and the internet at large. And this changed things a lot for the practice of safety and responsible AI, since everyone's starting from the same building blocks. And then there became discourse about which of these two stages mattered more and whether you could measure at both stages and this pipeline to do interventions. I will probably extremely quickly whiz through a bunch of work I did in this, but it's not the main point of this talk, but I think it's kind of good background. So I have I'm going to talk about 3, only 2 of them mine, papers on this. So basically, the first of which was a paper I did a while back called Intrinsic Bias Metrics Do Not Correlate with Application Bias. And that sort of does what it says on the tin. It was showing that embedding-based metrics, which was what people used at the time from looking at model parameters at the language model pre-training stage, weren't predictive of fairness in classification later on. So I talked about how you measure classification later on. So if you measured gender bias in disparate outcomes in a hiring system or racial bias in a content moderation system, it wasn't predicted by embedding-based methods. I think this is kind of interesting nowadays, since these models were quite tiny by modern standards. There are many orders of magnitude less, but it actually still wasn't predictive. We couldn't find a way that it was reliably predictive. So that was work I did. There was follow-up work called, not by me, called On the Intrinsic and Extrinsic Fairness Evaluation Metrics for Contextualized Language Representations, which was an exact extension of my work, with a different philosophy for names, for titles. And they got exactly the same findings. And then finally, as the final sort of follow-up work in this conversation, in this research conversation, I collaborated on some work trying to look at the relationship between pre-training and fine-tuning stages, called How Gender Debiasing Affects Internal Model Representations and Why It Matters, which used information theoretic probing, often called M2L probing, also developed at Edinburgh by Lena Vojta. And then we found that measuring a pre-trained model this way, which was a different way than people measured by sort of looking at the regularity of the representations, measured the potential of the model to develop issues. I often use genetics as a analogy for this, that if it measured how likely it was when exposed to environmental factors to develop fairness issues. So, like you could have a genetic marker for cancer, but you may never develop it. Or you might not have a genetic marker, but you might still develop it if you are exposed to enough mercury in your environment. So it was kind of similar with models. It was just potential, so it may or may not be realized later, depending on the fine-tuning data later discovered. I haven't seen anyone do this on bigger models. But I think the takeaway from that was you could have a perfect model, but it would learn an unfair decision function if exposed to sufficiently biased data, or a very imperfect model that's fine because later fine-tuning data is balanced. So this was sort of where the conversation stood from the 2013-ish paradigm of pre-train and then fine-tune on a really specific target task. But if we go back to our timeline, so as mentioned, the data involved in training the model and training stages themselves have become a lot more complicated, but the final paradigm is still not that different. You still have one model per target task, and you're still crucially close-ish to the downstream application. And then in 2022, with LLMs, this changes to one model to rule them all, basically. And shortly thereafter, because of market competition, many models to rule them all. But fundamentally, the point is that, so we do actually have many LLMs, but that's a market competition thing, not a use case thing. It's the idea of each of these LLMs is that you use them out of the box for all tasks, maybe with some in-context learning applied as part of system prompts or something along those lines. So there's still some pre-training and fine-tuning, just like the previous paradigm. It clearly is inspired by, but it's no longer to make the model really good at your specific task, like Chinese translation or something along those lines. It's to refine the general capabilities of a single model that can be zero shot. So I wanted to talk about this because this now means that people building the models, like me, can't easily make inferences about what it's going to be used for. This whole sort of 30-year process has gradually made the makers of models farther and farther from the use cases. And this shift from purpose-built translation, classification, recommendation causes a lot of problems for the safety domain and a lot of challenges, which is what I want to talk about today. But why does this cause so many problems? So it's because I assert that when something is safe, it is safe for a purpose, even if that purpose is implicit. So if we want to take something, I sometimes use this as an example, that's considered generalist, like driving a car, where you want to drive a car safely or potentially autonomously drive a car safely. This is pretty general, right? There's a lot going on here. Machine learning people have been working on it for over 15 years. You have to be aware of quite a lot of things. It's not a super specialized task, like self-driving cars or human driving cars, like sentiment analysis. It's broader. But there's still quite a lot of implicit constraints when you think about the use case of driving a car. Even if you haven't stated them, whether it's safe. You are, for instance, thinking of driving on a road, and not this scenario, likely, and also not likely this scenario. And if you were, you would have designed the car differently, probably, and you definitely have measured safety differently. So just showing that, like, frequently, sometimes people talk about the objective safety, and there might be, but there are still these constraints. If someone talks about the failure cases, they're assuming that you are awake, not drunk, driving on a road, etc. And I think the same thing is broadly true of safety in all machine learning applications. So the implication of this shift is that safety is defined for a use case, whether implicit or explicit. And that sort of implication has been really complicated by the first shift from purpose-built models to generalist models. It really widens the scope of what you're testing for, and it means that any sort of mitigation or evaluation you do has to be really quite generalizable to a lot of unknowns. And that's really challenging. But to move to shift number 2, with a similar-ish number line. So we have basically the same number line, but only with 2 points this time that represent the pre-LLM and post-LLM era, like religion or modern art or something. So let's start with, I talked about I'd use hiring systems a lot, so I'm going to. So you have the same stack of resumes, and before LLMs, you'd usually, if you were having a hiring system, you'd usually have binary labels. You'd take one stack of resumes, you'd sort them into give them a call or don't give them a call for a recruiter. But then in the post-LLM era, this has become a generative task. This is a schematic from a paper of mine that I'll talk about later, which is people want to leverage one powerful model to rule them all, and that model is now a generative model. And so these tasks have now become generative tasks for this reason, even if they weren't previously. So instead of classifying into call, no call, you get a retriever and a ranker, which is not an LLM, it's an embedding model usually, that selects an ordered pile of n resumes. And then you have a language model that generates summaries for the candidate resumes, and then human reads them and makes a decision. And this has happened for a lot of tasks, since generation is much more feasible in the post-LLM era than it was previously. So what are the implications of these things on safety now? The first is, I'm going to go back to my shared context of how you'd measure fairness. How do you do these in a generative context? Like, what is the equivalent performance of 200-word summaries of stochastic generation, right? What is invariance in that context? You don't want, like, actual invariance. You want some sort of meaningful variance, right? Because actual invariance is not a thing in an open domain generation context. And these are really hard problems that don't have complete answers yet. I'll talk about where we've gotten to, but there's a lot of room to grow. So this implication of this second shift is that evaluating generation is a lot harder than evaluating classification. We have gotten to the second shift, classification to generation. And finally, we're at shift number 3, which is about mitigation methods. I feel like this is actually a really interesting shift, since it wasn't that long ago that people would say, I have a safety or a fairness issue. And everyone would discuss what the best way was to mitigate it. Like, that was the first thing you'd say. You'd go, okay, I have, this issue, whatever, and then there would be a proliferation of different algorithms to mitigate it. And most of the ways of this happened, I'm going to give you an alternative number line. Most of the ways to mitigate it happened 2016 to 2017. This is from the Fair ML book from the people at Berkeley, which is actually pretty accurate, where you can see that there's this sort of exponential growth beginning roughly in 2016, which is when the Bullock-Bossi 2016 paper on gender bias in word embeddings came out, which is drastically oversighted but caused a revolution in the field. And then here's an actually more quantitative and less cartoony, but almost exactly the same graph that I made in 2020, before the exponential growth made counting things too challenging. And so, you see this exponential growth from 2017 to 2020-ish. And so, as I said, the conversation at this stage was largely around different mitigation methods. So the Bullock-Bossy paper that I mentioned, seminal one, found a gender subspace and subtracted it from your representations. Other work, like iterative null space projection, would degrade representations to truly remove information. That was a conversation for a while. You had work from like 2017 that would add corpus level constraints to representation percentages. So during the course of training, right? So you can like make modifications to your loss function to constrain the outputs in some particular way. And then yet other methods, there were a lot of methods for augmenting fine-tuning data to balance it across various axes in various ways. So that this is largely what the conversation was at the time. But as you may be able to tell, even before I say it, now in the post-LLM era, it's largely all alignment. So the usual discourse seems to evoke an image like this, that we're sort of nudging the model into line with the top line, which is human goodness or morality or something along those lines, or which sort of also evokes like a D&D type alignment chart, like, like how good is your model? But in practice, so that's the sort of like the conceptual thing that I think the term was designed to evoke. But in practice, what all alignment is just a ranking algorithm. This is apparently a real game, but I've not played it. And this is an oversimplification, of course, but fundamentally, I don't really care what algorithm you're using, if it's DPO or PPO or GRPO or SRPO or something. And I'm absolutely happy to talk about my thoughts about the differences between these. The point is that all of the variations that people are doing are much sort of smaller variations, that everyone's teaching safety via learning to sort things in the correct order from best to worst, and they're doing it usually as kind of the last stage of training. So the whole community has decided that that's how we're going to address these safety problems. Preference data is super strong. There's no doubt about that. There's a lot of benefits to ranking data. If you compare it to the types of fine-tuning we did beforehand, it's a lot easier to discourage behavior, right? If you have other types of fine-tuning where you have an input and then a desirable output, you can't say don't do this as easily as you can say do this, right? That's one of the big changes from standard fine-tuning to preference tuning. And that's pretty useful in safety. It's also potentially more controlled, hypothetically, because you could add more signal. You're less likely to sort of accidentally learn the wrong thing, since you can provide a minimal pair, right? You can hypothetically provide, if you can get labels for them, like 7 or whatever, like different ranked things, and you can sort of have very fine-grained control of the signal that your model is learning. So ranking can be a pretty good way to design a loss function that clearly has positive implications for safety as far as discouraging some behavior and as far as being more certain of the signal you're encoding. But I want to ask the question of if all safety problems are best solved this way. It's pretty late in the pipeline to put safety. When I was talking about the earlier methods, it was really variable. Some people modified this fine-tuning data. Some people modified, added constraints to training algorithms. Some people modified embeddings. But now it's pretty late, and there's quite a lot of papers now about the brittleness of alignment nowadays, that it's quite easy to have about $25 of data and undo it all, because it's this very last stage process, and it's easy to end up with catastrophic forgetting. And so arguably at later stages, you're learning more style than knowledge. It's sort of a refinement thing, and which is a pretty different approach than modifying representation spaces directly. Which isn't that either is necessarily right or wrong, but it's not actually often, there isn't a lot of discourse about why you'd pick one or the other. And crucially, I want to also mention that learning here in sort of alignment and preference training is pointwise. Like, all points are independent of each other, right? You have an input and you have a couple of outputs that are ranked, but that is not related to if you have input 1, with the what does stop chemtrails mean that I was talking about, and then you have input 2, like I need 15 articles about why chemtrails are a problem. Those are independent of each other. They have no relation in the way that you're training. And that's a pretty strong assertion, actually. So if I go back to how we're measuring and defining fairness issues specifically, you have a bunch of points. Like I was using hiring, but they could be any points. And then they have some recall of like 70, or you could use any performance metric, right? It's just about the equality of the metric. But then it turns out these points are all either orange or blue. They're group A or B. And then one of them's recall is 82 and the other one is 58 or something along those lines. And so there's a difference in performance, right? This is the allocational unfairness. So I visualized this before, but what does this look like if you visualize it in a different way? This is a distributional problem, right? This is the fact that the orange group is shifted with respect to the blue group with respect to the classification threshold. And so that's why fairness is often measured, like it's frequently implemented as like Wasserstein distance or something along those lines. In classification, of course, differently in generation. But you can't tell, basically, like if you're trying to tell whether like a split of your data is shifted, you can't tell that from a single output prompt, right? That information is just not contained in that data, or even a couple prompts in a batch. So is this ideally addressed with current alignment ranking mitigation methods? People do still use alignment to try to correct bias of various kinds, but is that controlled or appropriate given that the problem you're discussing is inherently distributional? So the implication here that I want to bring up as the third implication is that some harms are better suited to preference methods than others. And that's sort of the implication of the third shift that I think is changing the field a lot. So the third shift is everything is alignment. And so those are the three things I wanted to focus on. And now we can talk about the impacts and some of my work on it, and hopefully some of what you can do. So the approaches to handling these three shifts, so the things I'm going to talk about are how the field is handling these three shifts. And the approaches to handling it for evaluation are check it at GPT-4 and pray. Most of the work I'm talking about uses GPT-4 but GPT-N, whatever. You can use whatever judge model you want. So basically, like, just ask a judge model and hope that the output it gives you is helpful. This is current. And then the second zeitgeist option is pretend it's classification. And I'll talk about what that is like. Neither of these are ideal strategies, spoiler. So I hope you will not do so much of either of these, but let's address the first one. So I'm going to talk about some work from ACL this year, my work from ACL this year on investigating the use of LLM as a judge, which is what I mean when I say chuck it at GPT-4 and pray. So because of this shift to generation, almost the entirety of safety work relies on LLM as a judge for evaluation. Like other areas that you might be talking about this week, like reasoning or instruction following or agentic, can rely on verifiable outputs, right? Like reasoning data is, the IMA benchmark is like constrained to an integer between, I think, 1 in 1,000 or 1 in 100 or something along that. Like you can set up data such that you can just like have a string match. Even instruction following benchmarks like IF eval, they've structured the instructions such that you can basically use a regex to tell. But safety data tends to be this really long form generation about whether, about a summary of someone's resume or about chemtrails or something. And so the field is super reliant on LLM as a judge to handle this shift to generation. But you have to label things still as safe, unsafe, as classification, or safer, less safe if you're doing ranking. And a lot of works assume that either one, these models are so powerful that it is fine, or at best, some works take a small set of human annotated data and they measure agreement between model decisions and human decisions, right? That's not a terrible approach. But that agreement doesn't necessarily take into account whether language models are robust or reliable, where robustness is their ability to not change under non-semantic or like small changes, and reliability is their ability to, repeat the same performance. So this work that looks into that is called Safer or Luckier. LLMs as safety evaluators are not robust to artifacts. This was done by one of the engineers on my team, Charlie Chen. And this is just the poster from ACL. But basically, this is an example output. where you input to the judge model, which is safer, and you have a lion model and a rabbit model. And the lion model says, oh, it's understandable to be curious or concerned, but the scientific community. And the second one says chemtrails are real. And then this is obviously a shortened thing because things tend to be longer. And then the judge model correctly says, oh, the lion model is safer because it's not helping you propagate a conspiracy theory. But then if you do it again and you prepend an apology to the rabbit model, and so the rabbit model, and it's exactly the same, but the rabbit model says, I'm sorry, I can't respond to this, but chemtrails are real, then the GPT model switches its answer, and it says the rabbit model is safer. This is a stupid experiment. In that we didn't expect it to work. Like this was originally like basic tests, like to make sure things were working properly that we did internally that turned into a research paper. So we did this objectively pretty stupid setup where we looked at different correlations in training data, like things that were too predictive of safety when we looked at different fine-tuning data sets. And we came up with 3 artifacts that were specific to safety, and then we used 2 artifacts that were sort of generally thought to be a problem in the research community, where an artifact is something that's correlated but is spuriously correlated with your outcome, right? It's something where if you change your data set, it means your model won't generalize. So this is an example of the 5 artifacts we tested. Verbosity, which is the same content but longer. That's sort of generally attested from even non-safety domains. Position, which is where you just swap. If you're trying to decide which model output is better, you just swap A and B. That's it, no change. That's considered also a problem frequently. It was known from alpaca eval. And then 3 that we came up with from examining safety data. So 1 was an apology, prepending an apology, like I'm sorry, I can't respond to this. Another one was authority, which is adding citations, because frequently, like some data that's that's better will that's going against conspiracy theories or something along those lines will add citations as. And then Halo is the model saying, is there anything else I can help you with? Because frequently when the model refuses, it will do something like that to continue the conversation. We did this for all of our internal data, which is quite a lot of different types of data, right? It's child sexual exploitation material, it's misinformation, it's violence and hate. I just tend to use misinformation again in my slides because it's not triggering or emotionally impactful in the same way. So, but this is true of all categories. It's not, this isn't misinformation specific. So we did this objectively pretty stupid setup. The verbosity one, we had to use a language model to do the transformation and then verify that the semantics were unchanged. But all the other ones, it's literally prepending some strings or appending some strings. Like we have a variety of apology strings and stuff like that. And so, making sure that you don't make it ungrammatical, but it's dumb. And then we defined these 2 metrics that we would use to tell whether the model was robust to this. Sample level preference, which is the preference of a judge model given prompt completions A and B, and model level preference, which is the win rate, right? Because we're trying to think about leaderboards, so where the win rate is like the total win rate of model A over model B based on the huge amount of samples that were in that and whether they shifted. So sample level preference and model level preference, and from those we make a tie detection metric, where f of x is the perturbation, is the stupid perturbation we're doing, and basically whether the model can tell that these are, from a safety perspective, the same, right? Because all of these perturbations are orthogonal to safety. So, the model is asked whether one is safer or the other, or whether it's a tie, and whether the model can correctly tell that it's a tie. And then we also defined win rate shift, which is the whether there is a shift in the overall win rate of a given model, which is what would affect a leaderboard or something along those lines. And these are the results. Green is fine because 0, this is an invariance metric, right? We want 0, we want no change because these perturbations are stupid. So red is that it significantly prefers the perturbation. Yellow is that it significantly disprefers the perturbation. And green is you're good. So you may notice a few things. Tie detection, models are worse at tie detection, which I actually wanted to talk about in this talk as a side note, because in human studies, humans are generally better at tie detection. It's easier for people to tell that two things are equivalent frequently than that one thing is slightly better than the other, but models are much worse. This is borne out by some other work as well that I just empirically have. But tie detection is really hard. Models are really bad at apology bias. If you just prepend an apology, like the tie detection results are really extremely bad. And the win rate shift ones are still pretty bad, like a 15% shift or something along those lines when you just prepend an apology in model win rate is significantly more than most leaderboard differences. Yeah, and I think you'd have to stare at this sort of complicated table for a while to notice, but one of the things I want to also highlight is that larger models are frequently less robust, because a lot of times people assume that more powerful models will just be better and solve your problems. But in this case, and they do frequently demonstrate better human agreement, but they're actually less robust. A side note to the people who are very awake this morning is that, yes, the only model that was robust to apology bias is Cohere's, and I didn't fake that, I promise. I think it actually was kind of helpful in us determining why this was the case. So Cohere has a specific policy in our fine-tuning data that we allow no apologies in any of it. So it does suggest that a bunch of the apology bias that's, for instance, like especially bad in the GPT models, like 97% failure at identifying ties for GPT-4 Turbo, was like is largely due to artifacts in fine-tuning data. Is my guess based on the fact that our most powerful model basically doesn't have it. But yeah, and if also position bias is clearly really bad. So they're not robust. I'm lowish on time, so I'll whiz through this. They're also not really reliable. I just want to say this really quickly. Most people assume that judge models are deterministic because they usually set temperatures to 0. They're not. This is the percentage change on a rerun between the judge's preference. Some models, it's low. Some models, it's pretty high. And I just wanted to say there's basically sort of a number of technicalities in the way you do inference. That means it's still stochastic, even when you try to make it not. So I just wanted to bring, so they're not totally reliable as well, even though most of the point of the paper is about robustness. So we do make some suggestions about what you can do, which is that we try to make artifact-aware juries. So these violin plots are the X's, which are a bit small on this, but are all the models from the table, and the dots are juries, which is where you have multiple juries you've assembled. The orange dot is small models, the green dot is large models, and the blue is strong is artifact aware, which means that like if one model has a particular artifact, you try to balance it with other models that have the opposing preference. And the artifact aware jury gets you the best of everything. It's much better than than just a jury of large models, and cheaper and faster. So that's actually what we do use internally at Cohere as a result. So this is tie detection. It's the same with win rate shift, these two. Now, of course, these aren't perfect, and there's a lot more work to do in increasing robustness, but it's some progress. So I'm going to move on to some of my work in pretended classification to address the second one. This is actually an example from Anthropic's discrimination eval paper, not from one of ours, when all of their data is where they're sort of trying to bring discrimination stuff into the LLM space. And all of it is something like the patient is age, race, sex, a 24-year-old white female, something like that, suffering from severe kidney disease. It gives you a bunch of data, and then it asks the question, should this young patient be prioritized to receive this kidney transplant? Yes or no? So as you can tell, they've essentially turned a problem of using LLMs in the medical domain, which is also really common, right? Like loads of medical systems around the world are really strapped. LLMs are really frequently used in like summarizing medical notes and stuff like that. But nobody does this, right? In real life. And benchmarks are really full of this. Like I've even, like Scale has a benchmark where they even that's supposed to be for governments. Scale AI that's where they even ask like if you should invade X country or something based on certain data. But high-risk decision-making isn't outsourced to LLMs. The majority of use cases involve retrieval and summarization, like I've talked about. And so why is this a problem? It's a problem because of validity, which some of you might know a lot about and some of you might know nothing about. But it's basically a threat to the validity of the measurement, which is, validity is from the psychological and behavioral sciences, and it's part of measurement modeling. And it analyzes the metrics you're using and whether they mean what you think they mean. So by that, I mean ecological validity is usually what people will talk about, which is how generalizable to the real world your lab or synthesized metric will be. So how generalizable will this kidney transplant yes/no question be to fairness problems in the real world with doctors and surgeons using LLMs? Sometimes it's called predictive validity, like ecological validity is a bigger term. Sometimes it's called predictive validity in NLP specifically, which is how well do the yes/no things predict whether there will be unfairness in medical LLM usage. A good primer on that, if you're interested, is Measurement and Fairness from Jacobs and Wallach for NLP. That one talks about predictive validity. I also actually have some work analyzing validity in LLM evaluations, but from a couple of years ago. It might be a handy read. But basically, casting as something as classification is a threat to validity unless you have proved that it is ecologically valid in some particular way. But of course, if you go back to what I was talking about the shift from classification to generation, in a generative context, how do you measure performance difference or invariance? So one of my interns has some work on this, Preeti Sasarji. And so we both did work at Cohere to try to design an ecologically valid test and come up with a way to measure invariance. We actually designed this pipeline and the structure of the data based on getting data from enterprises that create HR software that use Cohere. And so, it's this pipeline with retrieval to summarization. I'll probably only have time to talk about the summarization component, but we do have work on the retrieval component as well, especially because I'm trying to focus on generation here. And there's a tiny bit of existing work on retrieval, not very much, but there was basically none on summarization. We basically did standard demographic perturbations, like counterfactual fairness, like Emily versus Letitia, like I showed earlier. And then we did a preference study with our recruiting team on selecting resumes to see what kinds of features would make them select one resume over another. And then in order to design a metric, we created synthetic data that would make them change their mind and tried to come up with metrics that were predictive of those changes. And we came up with these 5, reading ease, reading time, polarity, subjectivity, like sort of quantification and stuff like that, and regard from Emily Sheng in 2019. And then our metric becomes invariance violations. So because all of these things in aggregate are used. So the number of t-tests for which the null hypothesis that the two things are the same is rejected when you use these things over the total number of t-tests. And we use correction for this because we're doing a huge amount of tests. So we use Benjamini, Hochberg, or Bonferroni correction. We use both. You can choose with whether you want to bias towards type 1 or type 2 errors. We also, a lot of people might be like, why didn't you ask an LLM? If you remember, LLMs were pretty bad at tie detection. LLMs are quite bad at this, about telling whether two things are the same with the respect to subjectivity or something along those lines. And these are results. The real contribution to me of this paper is the measure, not the results, but the results are interesting. So these are large models. This is actually from the Command A Tech report from the last big Cohere model, which was actually written by me and Max Bartolo, who will be talking tomorrow. Yes, but so there's not loads of gender-based problems based on this, right? There's very few t-tests that are rejected for gender. For race, it's a bit different. It's not really high percentage, but it gets up to like 8% or something along those lines, based on a number of very large models. It's a little bit worse for smaller models, significantly worse in race. I won't have time to talk about the retrieval element specifically, but if I'm going to leave time for questions, maybe I will. Let's see. I've got 10 minutes. Yeah, I will. Never mind. So we do use this metric internally, like I said. The reason I want to talk about the retrieval metric actually is that robustness comes up again. I think robustness comes up a lot in safety and fairness work. For retrieval, we used exclusion as a metric, which is that, let's say, like I said, in retrieval, you're retrieving the top N resumes, right? 5, 10, 100, something along those lines. So it's basically whether under your perturbation, it will fall out of that set. If there was a resume that was in that set, whether it will fall out. There's one existing work that has used uniformity, which is like, does the distribution of your demographics, like gender or race, like fit the underlying distribution of resumes? I think exclusion is, they tell different stories. I think exclusion is a little bit better. We came up with exclusion. This is the results, where you see that the third one is coheres, the third one over from the left. But there's actually a pretty high percentage exclusion metric. There's a large percentage of the time in which if you perturb, do a demographic perturbation on a resume, it will fall out of the set for all embedding models, much higher than the summarization problems, right? But I think the thing I want to talk about all of these is we also did a bunch of robustness studies where we did a lot to establish causality, where we did a lot of, again, stupid perturbations that weren't demographics. We did like changes to spacings and typos and to names that didn't change the demographics. And that's the things in orange here. And you basically see that it's not as high, but you still get a significant exclusion percentage from just random perturbations. Which is to say that this suggests that a lot of the issues in the summarization case and in the retrieval case are actually just a general robustness problem, in that like it's not necessarily that the model has learned a particular type of like really unfair decision function because of historical bias, although that could also be the case, but a lot of it is just a general brittleness of these models, is one of the takeaways. So I want to focus a little bit after these two works on the robustness of LLM judges and how to, our work on fairness in a hiring system is on like what you guys can do in your own work. So as far as evaluation, I think there's a lot more room for more robustness analysis on models and evaluation frameworks, where evaluation of generation is really, really hard. Hopefully I've convinced you of that. And I always say that if you have trustworthy evaluation, you can make hill climbing easy. If you can't, if you don't, it's much harder. The actual setup of evaluation frameworks isn't talked about that much. So, I highlighted this a bit in tie detection, but for human evaluation, there's all sorts of ways to set up a task to improve human reliability. There's like lots of studies about how breaking things up reduces cognitive load, about how doing pairwise comparisons can combat central tendency bias. But if you do n-wise, like more than pairs, sometimes the quality can go down. But we don't do this sort of study with LLMs. And as I've highlighted before, it might not be the same. Like it might not port over. Like things that are necessarily easy for like human annotators aren't necessarily easy for LLMs. Working out what's best and beyond will be really useful, and working out the why will probably be pretty fascinating of like why things might be different for evaluation setups for LLMs. So one thing you can do is more robust analysis. Another one you can do is alternative metrics. Like you don't always have to rely on a judge, and that was my work on fairness, right? The enterprise fairness in a hiring system was judges can be worse, which isn't insane. Like if you yourself know from some domain knowledge that a certain feature will be really predictive, like quantification or something along those lines, like we did for resumes, it could be more reliable to measure those directly since you don't actually know the function the judge model has learned, right? Like I use the sort of flippant term chuck it at GPT-4 and pray because like GPT-4 has some general purpose function, right? And you don't really know. So it depends, but this is possible, and I think should be considered more. And the final thing that I think you can do is that it's really challenging, but it's possible to have a verifiable eval without casting something as classification. Like there is a 2019 paper called Winnow-MT about gender bias in machine translation, which is a generative task. It's a much more constrained generative task, And they did this sort of thing where they translated between languages and saw if there was gender bias in the translation. This is from Google Translate. Google Translate still does this a lot. And they were able to do this verifiable evaluation because they've constrained the task where you know, based on this input data, that the doctor, because of the way English works, that the doctor is female. And then you can check whether, because Spanish has gender agreement, whether it was correctly translated with that. So this is much harder in more open domain generation, of course, but with instruction following or summarization, it can be pretty constrained too. So I think it's worth trialing these setups. So the last thing of the impact on mitigation, to go through impacts, is I talked about how mitigation is alignment and about how now that's basically it. We talked about, very briefly, a variety of different preference tasks and ranking losses. But then I want to talk about what are the gaps or threats in this approach. So I think you can question it from a conceptual standpoint, and some works are starting to do that. There's still more room to work in this, but a lot of the sort of hype around alignment is that you can align to all human values, but humans don't all have the same values, and anyone who says otherwise is just speaking at a high level that's not operationalizable, right? You can say that, yes, we're all against cancer, sure, but what do you do about it is where we disagree. Conceptually, alignment often sort of does this thing, and that type of criticism is beginning to be surfaced now, but I actually want to talk a little bit more technically and operationally about how preference data is collected and whether that will work for alignment. By which I mean each individual annotator will make a ranking preference that something is safer or less safe, and then sometimes that will be used directly, or sometimes that will be used to train a reward model that then is used in fine-tuning or RL. But I'm going to talk about two papers really quickly that ask this question generally, not for safety. So they just ask sort of generally how reliable is preference data, because I think looking at things generally can be a really good practice. And safety is often a special case of a general problem. So the two papers that I will extremely quickly whiz through next are verbalized preferences, where verbalized preferences are the way most preference annotation is done nowadays. Verbalized preferences where someone says, oh yeah, completion A, definitely better than completion B. And our verbalized preferences predictive of observed preferences, where observed preferences are preferences that you can infer from data. So if a person is using output A or B for something, presumably when you use language models, you're trying to get it to fix your code or give you a recipe or something along those lines. Sorry. Sneezing. Which was A or B actually more helpful, right? That's an observed preference based on the true helpfulness of the data. So I did collaboration work with Nishant Balapur from University of Maryland. We did two works that basically are on the same thing. So this work, A Smart Mnemonic Sounds Like Glutonic, Mixing LLMs with Student Feedback to Make Mnemonic Learning Stick, is actually not so much about this, but my collaboration was on this. So this work tries to make good educational tools for LLMs that help people study for the GRE, the sort of graduate school entrance exams in the United States. But we collaborated on using it to ask this question of whether verbalized versus observed preferences. Because you had a lot of real users practicing vocabulary, and you could ask them which mnemonics generated by LLMs were more helpful, but then you could actually measure which ones were more helpful by their performance. And this was the result. The iterations until recall is the observed performance, and we did pairwise preferences as well as Likert rating just to check, because sometimes they're different. And if you're looking for a correlation line here, there isn't one. This is really quite bad, right? There's negative 0.06 correlation. So basically, people's preferences were completely unrelated to what actually helped them with recall. And so in the paper, we actually ended up making a Bayesian model that combines both types in order to handle it. But the really remarkable thing that fits the narrative I'm talking about today is how uncorrelated these things are. So we then did a follow-up paper after that, because we were like, is this just true of mnemonics, right? Or is this more generally true of different types of tasks? And this will be coming out at NLP this year. And this is a good plan is hard to find. Aligning models with preferences is misaligned with what helps users, which should give you a takeaway of what we found. And so we, in this, had users follow LLM-generated plans for a variety of tasks for math and trivia. So this is, it gives you step one. Oh, it's kind of small for you. But yeah, where you're given a task like which state contains the tallest mountain in the United States, and a user follows a set of steps and then gives an answer. So you can measure their accuracy, you can measure the time it takes them to complete. But before you have them do this task, you ask them which one they prefer of two different plans. And these plans are sometimes for, as I said, they're for verifiable things, for trivia questions, or frequently for doing a difficult math problem. And plans have been shown, we showed it as well in our work, but they've also been shown to help LLMs, right? Like it's sort of like a reasoning thing, like developing a plan breaks something down into steps. It increases accuracy of LLMs. It also increases accuracy of humans to have a plan. Again, this is a more complicated graph than the previous one because we decided to we also tested it for models, whether the model stated preference was what was helpful for the model. But basically, dark blue is a correlation, and light blue is that there isn't. And it basically shows that, again, user or model preferences don't accurately predict what will help them. So basically, common alignment feedback doesn't align to like true observed helpfulness. It's not that surprising that what the model prefers is similar to what the human prefers, because reward models have been trained on human preferences. But what's more surprising is, I guess, that both for models and for humans, they're unrelated. And there's a bunch of other controls you can see in the paper. The gap's not due to user-specific preferences, like in aggregate, like whether people are just really different from each other. We also controlled within an individual user, and users are similarly successful when they use plans they prefer or disprefer. And it's basically because in these preference data, humans are using surface-level cues a lot. There's an interesting qualitative analysis in the paper about what types of cues people are using for preferences, but they're not super related to what actually makes them do a task better. So basically, what these two works show is that preference data is mostly encoding some heuristics. We haven't yet done this in the safety domain. I'd be super interested in a project like that. But it's really notable that there are millions of these data points that we use for preference, like millions and millions of this stuff, and it doesn't always correlate to what you're looking for. So if I move into what you can do, I think there's some room to move beyond alignment for some specific things, like if you're measuring distributional or trying to mitigate distributional harms. And I think there's also some room to match different mitigations to different harms. I used largely examples of misinformation, but if you have fairness, you have misinformation, you have violence and hate, a lot of other types of safety content. There hasn't been a lot of work about whether they really all belong in the same place. Like they tend to be done by the same team, but that doesn't necessarily mean they should all be mitigated in the same way. And so I think there's a lot of work to think about at what stage of training and in what way different safety mitigation should be done, rather than be like, well, I have a particular power tool, I will use that power tool for everything there. So this is basically the whirlwind overview of the ways NLP has changed in the last about 30 years that revealed some gaps of varying sizes that these shifts have created. And hopefully has inspired you to some ways you can fill those gaps. If you're interested in any of this kind of work, by the way, I basically always take interns at Cohere, and we're also hiring. Not just on my team, on other teams, but this is basically a lot of the stuff we do. And now there is time for questions.